An exponential equation is an equation that has an exponential expression in it, meaning that the variable appears in the exponent. A polynomial equation might have an expression like x squared, whereas an exponential expression would be something more like 2 to the power x. The way that we handle these is very different algebraically. What we really need in an exponential equation is a way to get the exponent out of the exponent and onto the floor. So to get that, in this case, x minus 1, out of the exponent and on the same level as the other terms. The way we do that is with a log, but we have to follow these steps in a particular order. The first thing that we do is we isolate the exponential expression. The exponential expression is only a base and an exponent. There can't be anything else multiplied by it, added to it, divided, right? Nothing else can be on the same side as that. So our exponential expression in this case is this whole piece 5 to the power x minus 1. The way we can isolate it in this case is just by subtracting 2. Very simple. So subtracting 2 from both sides gives us 5 to the power x minus 1 on the left and 10 on the right. I now look and I can see that 5 is my base, x minus 1 is my exponent, so I have isolated the exponential expression. Now I'm ready to take a log or a natural log of both sides. I don't have to match the base of my exponential expression. So this exponential expression has base 5. There's no need for me to take log to base 5 of both sides. I can go ahead and take log to base 10 of both sides, and we'll see what happens when I do that. So I'll take a common log and a common log. That's log to base 10. And that gives me log of 5 to the power x minus 1 on the left and just log of 10 on the right. The reason I don't have to match the base is that we have a property of exponents that allows me to take something in this form and bring the power outside as a scalar multiple, so that the x minus 1 comes down to the floor level, which is really what we needed. So I now have x minus 1 times the log of 5. And it happens in this case that I can evaluate the log of 10, but that wasn't an important part of this at all. Sometimes this has to stay inside a log, and that's something we put into a calculator in our very last step. In this case, because the log of 10 is simply equal to 1, we can simplify it. And at this point, all I need to do is just finish solving. So we've done the take the log or ln of both sides, and we now finish solving, and what this means is whatever equation we have at this point, it could be linear in most cases, it could theoretically be quadratic or something if I happen to have an x squared up there in that exponent, but I can now just solve it as a regular equation. It's no longer, the log is not really relevant to the class of equation because the log is just taken of a number, and log of 5 is a number. So what I'm going to do here is just divide both sides by the log of 5. And that gets it canceling from the left-hand side. And I now have x minus 1 equals 1 over the log of 5. And finish solving for x by just adding 1 to both sides. So that my exact solution, there's only one solution, it is 1 over the log of 5 plus 1. For a decimal approximation, I'll need to put this into a calculator. We don't want to get decimal approximations along the way. We want to wait until we're done solving so that we have one expression to enter into the calculator. So I'm going to have 1 divided by, in this calculator I would hit 5 first and then hit log to base 10. And then I will finally add my 1 to get 2.43. If I take this to 3 decimal places, that 0 will round up to a 1. So I have just one solution. Exponential equations have lots of applications, so we'll just go ahead and shift straight to applications and get some practice solving exponential equations there. In this compound interest example, we are talking about interest compounded annually. Since it's not compounded continuously, that tells us that we want this formula here. Amount equals principal times 1 plus the rate divided by the number of compoundings to the power nt, where n is the number of compoundings and t is time in years. So in this, an investment of $1,000, that is my principal, to grow to $8,000, that is my amount, at a rate of 9.5%, that gives me R as a decimal, that would be 0.095. And the question here, how much time, suggests that the thing I don't know is really t. We can already see how this is going to become an exponential equation because my unknown t is in the exponent. So I'll go ahead and start plugging into this formula. 8,000 equals 1,000 times 1 plus 0.095. The only other thing I didn't identify in this information is the number of compoundings per year. Annually means n is equal to 1, which means we can essentially ignore the n's in this particular formula, since multiplying by 1 and dividing by 1 both have no effect. So this is the equation that I get, and I'm going to go ahead and simplify the base of this exponential piece here. 8,000 equals 1,000 times, that's the same as simply 1.095 to the t. Now remember that when we solve an exponential equation, our first step is to isolate the exponential expression. That means I can't have this 1,000 on the same side as my 1.095 to the power t. I have to get it out of there first. The way I get it out of there in this case, since it's multiplied, is by dividing both sides by 1,000. So that on the right-hand side, it cancels, multiplicative. And on the left-hand side, I am left with just 8. So that my equation reduces to 8 equals 1.095 to the power t. At this stage, I am ready to take a log or a natural log of both sides. You can use either common log or natural log. Most of the time when logs are new, students are more comfortable with the common log. So I'll go ahead and use the common log anytime my base isn't e. If my base is e, it really is going to simplify things a bit to take the natural log. But for now, I'll go ahead and just, whoops, I didn't leave quite enough space for that, did I? Take a common log of both sides. Okay, now my variable t can come down by this property of logs and become a scalar multiple of the whole log. The log of 8 can't be simplified, but that's fine. We'll just leave it as log of 8 for now. So this now says log of 8 is equal to t times the log of 1.095. And now we can solve this for t. This is just a linear equation at this point. We can solve this for t by dividing both sides by the log of 1.095 so that we get t equals log of 8 divided by log of 1.095. And I am ready at this point to put this into my calculator. So on this particular calculator, I'll say 8 log and then divided by 1.095 log equals 22.9. Let's go ahead and, since this is a number of years for an investment, we'll just take it to the 10th. That seems to be plenty of accuracy. I'm going to say 22.9 years. Remember in the compound interest formula that time is always in years, assuming that your interest rate was an annual interest rate, which it typically is. So we've got 22.9 years for our investment to grow. On this example, we are working with doubling time. And note that this also says compounded continuously. So we want to notice that right off the bat that we're now working with the formula for interest compounded continuously, which is A equals P times E to the RT. So this is the formula we're going to use. Let's pick out the pieces that we know. We're definitely given an interest rate of 8%, which tells us that R is equal to 0.08. We're asked for the doubling time, which first suggests that time is going to be our variable. We don't know t. The thing is, we're not given values for a or for p in this case, but the doubling gives us a hint. Doubling implies that a is going to be twice as big as p. Now there are a few ways that we can use that information. We could just choose dollar amounts. Like for example, let's say we start with a principal of $1 and we end with an amount of $2. This will work. The idea of a doubling time implies that it doesn't matter how much your principal was and how much it doubled to. As long as it doubled, that's going to be the same amount of time just based on this rate and this compounding. We could come up with numbers that maybe look a little more reasonable, like 100 and 200 if we want to. Another thing we could do is just leave p as a variable and say that a is equal to 2 times p. Any of these approaches will work and they will get us a doubling time. I'm going to go with the second one just because mathematically it's a little bit more precise. So what that means is I'm going to put in 2p on the left and leave p as a variable, and I'll put in my 0.08 for r. Remember that e is actually a constant, so it's not a variable even though it's a letter. We don't need to worry about having something to plug in for it. In our first step now, when we try to isolate this exponential expression, we would do that by dividing both sides by p. And we can now see why it is that it doesn't matter what p is. It cancels out from the right, but it also cancels out from the left, leaving us just 2. So we get 2 equals e to the 0.08t. And this equation we're going to solve for t using the same methods we've been using. This time I'll take a natural log of both sides. Since my base is e, I don't have to match the base, but it does make things a little bit cleaner if I do. I don't have as many things to write. So on the left-hand side, I still just have the natural log of 2. And on the right-hand side, since I'm taking a natural log of a power of e, those are inverse functions, and I'm left with just 0.08t. I don't have to use that property of exponents like I used when the bases didn't match, because this is something I can actually evaluate. That's why we chose to match the base, but I would only match the base if your base is 10 or e. It's not really worth the trouble otherwise, since your calculator isn't going to be able to evaluate it without changing the base later. In this form here, we just need to divide both sides by 0.08 and we'll be done. So let's go ahead and enter this into our calculator. 2 natural log divided by 0.08 gets me 8.664. Let's go ahead and write this as 8.66. And again, this is a value of t, and therefore this is a number of years. We'll also take a look at an exponential decay model. If we recall our exponential modeling using half-life tricks, we know that this formula, a of x equals a naught, that's our starting amount, times 1/2 to the x over k is a general model for anything with a half-life, where k is the half-life. That can get us to this formula here for this particular application, which would be T of X is the amount of tritium in grams. So in this case, it looks like we're looking at units of years. The half-life is 12 years. Therefore, X is time in years. So, to address this question of how much time it takes for the amount of tritium to decay to 5 grams, we can see that 5 has to go in for T of X, not for X. So I would set up this equation here. 5 is equal to 15 times 1/2 to the power x over 12. And we want to solve this for x. A fairly common mistake is to come along and try to combine the 5 with the 1/2 by multiplying them. We can't do that because note that 1/2 is taken to a power. I'm sorry, I said 5, I meant 15. 15 is not taken to that power. So we really can't combine these two. What we need to do instead is what we've been doing in our first step, which is to recognize that this is my exponential expression. This has a base and an exponent, and anything that isn't part of that needs to be moved away. So I will start by dividing both sides by 15. And that gives me 1/3 when I reduce it equals 1/2 to the power x over 12. At this stage, I'm ready to go ahead and take a log of both sides. I'll go back to common log now since I don't have a base of e. This expression is a little longer, so I'll use the square brackets. We've got 1/2 to the power x over 12 equals, and again we're using this property of logs to bring down the power and write it as a scalar multiple in front of the log. So this becomes log of 1/3 equals x over 12 times log of 1/2. Now I have two operations that I need in order to get x alone on one side of the equation. I can do them all at once if I'm comfortable with it. If not, go ahead and do it in two separate steps. So maybe the first would be to divide both sides by log of 1/2. Which does allow me to get rid of the multiplication by log of 1/2. And then I have just x over 12 on the right-hand side equal to this whole thing, which I don't necessarily want to write again. At this point, I would multiply both sides by 12. Actually, I'll go ahead and write it again now with the 12 in there. So it's going to be 12 times the log of 1/3 over the log of 1/2. And that is the expression that I'm going to enter into a calculator. So 12 times 1/3, whoops, let's start that over again. 1/3 log times 12 divided by, let's say, 0.5 log is equal to 19.019. So let's say 19.0. And again, this is in units of years. So we're going to say 19.0 years. At the end of one of these exponential applications, especially the decay applications, because they're fairly easy to visualize, it's a good idea to do a ballpark check to see if this seems about right. So what we know about this context is that tritium has a half-life of 12 years. So that means if we start with 15 grams, after 12 years, we expect to have half of that, which is down to now 7.5 grams. After another 12 years, we expect to have half of that amount, which is now down to 3.75 grams. The amount that we're looking for the tritium to decrease to, which is 5 grams, is somewhere between the 7.5 and the 3.75. And note that the 19 years is also somewhere between 12 and 24 years. So it does at least look like it's bounded between the appropriate two numbers.